Welcome again. Today we start our next topic, representation of graphs and trees in computers. First, graph representation. There are different data structures for the representation of graphs used in practice. First, adjacency matrix. It's a square matrix of size V square, where V is the number of nodes or vertices in the graph. So if we have 4 nodes, then the square is 4 by 4. 5 nodes, the matrix is 5 by 5. In the adjacency matrix, the rows represent source vertices and columns represent destination vertices. So if we have a path from the source to the destination vertex, then we insert 1, otherwise we insert 0. For example, the adjacency matrix for the undirected graph here on the left is below. As you see, from 1 to 2 we have edge, so we have 1 here, to 3 as well, but to 4 there is no edge, so we have 0. Adjacency matrix can be applied to a directed graph as well. Here is an example, directed graph, and this is the adjacency matrix for this graph. From 2 to 0, no edge, to 3, no edge, but there is an edge from 2 to. Adjacency matrix is easy to implement, but the major drawback is the space complexity. We need V square cells in the adjacency matrix. Next, adjacency list. Adjacency list is the array of linked list, where array size is the same number as the number of vertices in the graph. Here we have 4 nodes, so the size of the list is 4. Each node in the linked list, in this linked list, represents the reference to the other vertices which share an edge with the current vertex. So 1 is connected in the graph on the left. 1 is connected to 2 and 3. 2 is connected to 1, as you see, and 4. 3 is connected to 1 and 4. 4 is connected to 2 and 3. It can be applied to a directed graph as well. Do you see 1 is connected to 2 and 3, 2 to 4, 3 is not connected to anything, and 4 is connected to 3. Really, additional data can be stored if edges are also stored as objects. Here is an example. We have the undirected graph. This is the adjacency matrix of size 5 by 5, 5 rows, 5 columns, as you see. And this is the adjacency list for this graph. We have 5 nodes and a linked list indicating which node is connected to another node. For example, 0 is connected to 1 and to 4. 1 is connected to 0 and 4 and 2 and 3, etc. Here is an example for directed graph. We have the directed graph. This is the adjacency matrix representation, and this is the adjacency list. A is connected to B and D. C is connected to F and E, etc. Here is a comparison between the matrix representation and the linked list representation. Linked list representations are used to save space. In the matrix, the space complexity is B square, where B is the number of vertices or nodes. But in the linked list representation, big O is just the number of vertices plus the number of edges. So using linked list representation, we save space. In the linked list, adding a vertex is easier. In the matrix representation, removing an edge takes big O time. Queries are faster and searching. Linked list supports sequential search only. This is one drawback of using linked list representation. Next, incidence matrix, which is usually used for a directed graph, has B rows and E columns. So the rows represents the vertices and the columns represents the edges. Do you remember in the matrix representation, the square matrix was of size V square. Rows and columns represents vertices, rows source vertices and columns destination vertices. Here, rows represents vertices and columns represents edges. The element Aij in the incidence matrix A is -1 if Vi is the final vertex of edge Ej, 1 if Vi is an initial vertex of edge Ej, and 0 otherwise if Vi is not incidence on edge Ej. I will demonstrate this through an example. Here we have example. We have a directed graph with 4 vertices, 1, 2, 3, 4 in the rows, and 6 edges, A, B, C, D, E, F. We start filling the matrix as follows. Now, node 1, regarding A, the edge A, it's a outgoing edge, so we insert 1, B as well. HC is not incident to node A, D as well, E as well. Do you see? It is a destination node for HF, so we insert here -1. Now, for example, node 3 here. It's not incident to edge A. It is a destination for edge B -1, and it is source. The node 3 is source for edges C and D. So we insert here 1, 1, and it's not incident to edges E and F. Features of incident matrix. It can be applied to any directed graph. The sum of any column equal to 0. Here the sum is the sum of any column equals to 0. As you see, the sum here 0, 0. In and out degrees of any node can be calculated. For example, if we take node 3, do you see the n degree of node 3 is 1 here, minus 1 represents the n degree. The out degree of node 3 is 2. Here we have 2 ones. So sum of minus 1s in any row represents the n degree of the node, and the sum of ones in any row represents the out degree of that node. Additional feature of and good feature of incidence matrix that we can remove any row. We can delete any row, anyone, since we can restore the contents of that row. Next, binary tree representation. First, array representation. We can represent a binary tree using arrays, one-dimensional array of size, of maximum size 2n+1, n is the array, is the tree depth. For example, if we have this tree, we fill it A, B, C, D, E, F, G, H. Do you see? We have to follow the formula. Left child is at position 2i+1, right child at position 2i+2, and parent at floor of i-1/2. Here, if we take node A, the root, if the index starts from 0, according to this formula, left child is at position 2 multiplied by 0, 0 plus 1. This is the left child. And the right child at position 0 plus 2, 2. For example, C here at position 2, the left child is at position 5, and the right child at position 6. If the index in the array starts at 1, not at 0, then you have to remove 1 from here and decrease 1 from here and remove from here. It depends whether in the programming language the array index starts from 0 or 1. Please be careful on filling the array elements. For example, giving this complete binary tree, it's wrong to write ACD, since this formula will not hold. In order for this formula to be true, we have to fill in this manner: A dash C, and the right parent of C is at position, as you see, 2i+2, should be at 6. Next, linked list representation for the tree. There are different forms using a node with 2 fields, one form, one field for the data and the second for the reference, and there are other forms using 3 fields, data left, right, or data left-right sibling. I'll show you. This is the tree, and this how we can represent it using a linked list where each node has two fields, one for the data and another for the reference. For example, if you see node C here, reference to G on the left and to the H on the right. Here is a linked list representation where we use three fields on the node data, left child address, right child address. This is similar to the tree itself. This here A, the left child address points to B, and the right child address points to C, etc. This is another form of representing a tree using a linked list. It's called data left child right sibling. So here is the left B, the left child of B is D, right sibling is C. You see on the previous we use node left child data right child, but here we use right sibling. These are the different ways used to represent graphs and the trees. Selecting the proper way depends on the application and on the operations to be performed on the trees and on the graph, and as I mentioned, depends on the space available. Since linked list representation saves space but slower in traversing, since the search is sequential. Thank you.